Hello, class. Welcome back to week 2 now of class. I hope you are ready with your coffee and your pen and you're ready to take notes and learn some more. So we finished off last week talking about bonds and the different types of bonds. We talked about covalent bonds and ionic bonds, and we finished up with hydrogen bonds. And when we were talking about hydrogen bonds, we talked about how those are really strong in water, right? So that's what binds molecules of water to one another. So we're going today now to talk about water and then some other types of larger molecules, macromolecules that are important to biological systems. So the things we're going to be talking about today are we covered our atoms and bonds, so we're going to talk about water, and then I think in this lecture we'll get through carbohydrates as well, and then we'll pick up, we'll see what the time looks like, we'll pick up with some of these other molecules a little bit later. So as everybody knows, water is really important for life, right? And we don't know of any organisms that can survive without water. So if you've heard of like probes, to the moon and Mars, they're often looking for water, either in frozen or liquid form, to indicate that there could have once been life there. So water has, in addition to the fact that we drink it, it has a lot of really important other life-supporting properties. And that's what we're going to talk about today. There are 4 important properties of water. And we're going to go into these in detail. One is cohesion. The other, number 2, is the high heat capacity. Then number 3 is that it's a low density when it's a solid. And number 4 is that it's a good solvent, and that's because it's polar, and we'll talk about what that means when we get there. So the first property is cohesion. Cohesion is stickiness. And water molecules bond to other water molecules. This is what we learned about just the last lecture when we talked about hydrogen bonds, right? So if you have, one water molecule here, and these are hydrogens, and you've got your big oxygen in the middle, these are covalent bonds within a water molecule, but then they are hydrogen bonded to other water molecules, right? So the water molecules themselves are stuck to each other. So the fact that these water molecules are stuck to each other enables them to create like a surface. So this is surface tension that you may see bugs walking on, which we had that picture right before this here, right? A bug walking on it. That's because all of those molecules are stuck to each other. It also enables molecules, one water molecule, to pull the molecule that's coming after it. So this enables them to transport water all the way up a tree, right? Trees don't have pumps. They don't have a heart pumping water from the ground to their leaves like 50 or 100 feet in the air, right? This is all because of cohesion, that water is able to move through an entire organism. And you've all seen this before with your shoelaces, right? If you have a shoelace that's kind of hanging down and it gets in a puddle, it'll wick the water all the way up and your whole shoelace gets wet. That's because of cohesion. Okay, the next important property of water that we're going to discuss is a high heat capacity. This means that when you put energy or heat and energy are the same, and we're going to talk about this in the next chapter. When you put energy into the water, it doesn't automatically get hot. So it takes energy to break bonds, right? And that's why some bonds are strong, like covalent and ionic bonds, and some bonds are weak. We talked about that, right? A weak bond can get broken easily. And a strong bond takes more energy to break it, right? You have to really put a lot of effort into it. When energy is put into water, heat is put into water, it will break some of those hydrogen bonds that are so easy to break, but then they just reform again. They don't stay broken. So you do have to keep putting more and more energy into the water in order to break apart all of those water molecules from each other. And so water, you can put a lot of energy into water before its temperature goes up, right? So the ocean takes a long time to heat up. And you've all seen this if you're trying to make a pot of spaghetti, right? You turn on your stove and you wait forever before it seems like it's boiling, right? It takes a long time to boil that water. And that's because water has a high heat capacity. It can absorb a lot of energy before its temperature goes up. This is important for life, not because all organisms need spaghetti, but because the water is actually moderating the temperatures of the whole world, the planet. So it's absorbing a lot of the heat, especially the excess heat that humans are putting into it now. Our oceans are absorbing a lot of heat, and then they give it off slowly. So it ends up moderating temperatures, kind of like the Earth's thermostat. So areas that are near the ocean are often warmer in the winter because the ocean can be giving off a little of that heat that it absorbed over the summer, and then cooler in the summer because the ocean is absorbing some of that heat. It also can moderate temperatures within organisms themselves. Organisms like humans have a lot of water in them, right? A lot of organisms are made, the cells themselves contain a lot of water, and so that helps moderate internal temperatures. Okay, so that is our important property number 2, was our high heat capacity. Okay, let's move on to property number 3. This is that water has a low density as a solid. What does that mean? That means that it's light. When water is in its solid form, it's lighter than in its liquid form. While that may seem obvious to you, that's different from most other molecules. Most molecules get denser as they become more solid. Substances are just made up of lots of molecules, and as they cool down, the molecules move slower, and when they heat up, they start moving around really fast. Usually, as they start moving slower, they kind of pack tighter together, and that makes them heavier. But the water itself forms a lattice, right? Its ice is this nice crystal structure that you see down here, right? It has these big air pockets in it. So water is less dense when it's a solid and it floats. You've all seen that if you put ice cubes in a glass of water, right? The ice cubes float, they don't sink. So why might that be an important quality? Think for a moment about water and why it might be important that it floats in its solid form. Okay, that's actually going to be our discussion question for this video. All right, so I won't give you the answer yet, but I'll be monitoring it and let you know. Okay, so then our fourth important property of water is that it is a good solvent. And this means that things dissolve in it, which you know, right? You can make sugar water, you can put salt in water, right? Lots of things dissolve in water. The water that you get from your tap isn't just pure H2O. There's a lot of stuff in there. There are important minerals. There can be chlorine, right, to help to purify it, right, and make sure there's no bacteria in your water. There are lots of different things that can be dissolved in our water. And this is because water is polar. So polar means it has poles. And in this case, it has some positively charged and negatively charged. And why is this? Because of the hydrogen bonds, right? So here we've got our hydrogens and our oxygen, right? And actually these are covalently bonded, right? But remember that hydrogens, because they're so tiny, they're not holding on to that electron quite as strongly as the oxygen is. So our hydrogen becomes slightly positive because the electron is really a little bit closer to the oxygen, right? And the oxygen is slightly negative. That's what it means by polar. This one molecule has a positive end and it has a negative end. And that's how it can bond to other water molecules, right? We've got this, if we have another water molecule here, and this is slightly positive, this positive hydrogen and this negative oxygen form a hydrogen bond to each other. So water molecules can therefore break ionic bonds of other molecules and they can dissolve in them. So anything that is also polar can dissolve in water. Non-polar molecules like oil obviously will never dissolve. You can't mix your oil and water. If you've ever tried to make salad dressing, you see that, right? The oil is always going to float to the top. But you can dissolve sugar, you can dissolve salt by putting energy in, right? And that energy could be heat, or it could just be stirring. That's putting energy in too. So here we see NaCl, sodium chloride. This is just table salt. And this is how water can dissolve table salt and kind of break apart the Na with the Cl, and they each become surrounded by water. Now, water can also be an ion, right? We talked about ions being something that is a positive and a negative, because you could take one of those hydrogens and pull it off of the water. If you did that, you would end up with one H that's a little bit positive, and then the other half of the water would be OH, which would be slightly negative. When water is broken apart like that, that's actually how we measure pH of things. Everybody here has heard of acids and bases, or the pH of things. This is just a measure of whether there's more H plus in a water system or more OH minus. Pure water, if you just have absolutely pure H2O, it has a pH of 7. And the pH scale goes from 1 to 14. So 1 is the lowest number on it. And I didn't write 14 on here, but I have a picture next. 14 is the highest. So things that have a low pH are acids. So that's below 7. And a high pH are bases. And that's above 7. A difference on that pH scale is huge. So it's not like a linear thing where it's like a difference of 1. It's like, oh, well, whatever, it's not that big. This is a log scale, which if you remember back to some of your, high school math, a log scale means a difference of 1 is actually 10 times more acidic or 10 times more basic. A difference of 2 is 100 times. So whatever that difference is how many zeros you're going to add to it. So a difference of 1, you add 1 0. A difference of 2, you add 2 zeros. A difference of, here I've got 4, right? You're going to add 4 zeros. So let's look here. We've got a picture of this pH scale. So it goes from really 0 to 14. 7 is the middle. This is our pure water, nothing in it. Okay. If you compare urine to pure water, there's a difference of 1 on this. Urine is a pH of about 6. So a difference of 1, it's not just 1 times more acidic. It's actually 10. Urine is 10 times more acidic. So these are all acids, and these are bases. Okay, you may have heard that with climate change, the ocean is becoming more acidic. Well, let's look. The ocean is supposed to be, seawater is supposed to be basic, right? Here we are at the ocean. Becoming more acidic means that the pH is lowering in the ocean. Organisms that live there have not evolved and adapted to live in a more acidic environment. So if the ocean went from a pH of 8 to a pH of, let's say it went down to 4. It's not going anywhere near that low right now, don't worry. But just, for our math and testing purposes here, let's say it got down to a pH of 4, to tomato juice pH. How many times more acidic has it become? Well, 8 minus 4 is 4, right? So now we need to add 4 zeros on there. It's now 1,000 times more acidic. And you can see like coffee is a pH of 5. You may have heard that people who have like acid reflux shouldn't drink coffee, or if they have ulcers. That's because it's so acidic. But look at how acidic your stomach already is. It's a pH of 1. That's super acidic. And then we get into bases as we go up from 7. So you can see bases tend to have a more slippery feel. So soapy water, bleach, if you've ever put your hand in like a bleach solution, it's really, really slippery. Um, Baking soda. I'm here to tell you, anybody who's seen like basic water being sold, people say it's supposed to be healthier and you can pay like, $5 for a bottle of, basic water. You could also just put baking soda in your water if you wanted, and it would cost you about 2 cents. But also your body regulates pH very, very carefully. And you could drink all the baking soda water you want or all the lemon juice you want. And unless you have your blood pH is not going to change. Your body is controlling that. So those are just total gimmicks to make you part with your money. Don't buy basic water. Okay, so if you've got any questions on acids, bases, write them down, put them in the discussion. And from here, we're going to move on. And we're now going to talk about some carbon-based molecules. So we've done a lot of talk of bonds and water. And we're going to talk about molecules that are made of carbon. And we're just going to do a few for this video, and then we'll take a break and move on to the next. Okay, so the first molecule that we're going to talk about are carbohydrates. And when you think of a carbohydrate, let's first think of like what it is, what's in a carbohydrate. And we can look first at this chart of the elements in the human body, right? Oxygen is a big one, carbon, hydrogen. Those are the top three. So if you're ever asked, what do you think might be the elements in this molecule? Carbon, hydrogen, and oxygen are always going to be the top three. And then other things kind of get added onto that. So a carbohydrate, if we think of the name carbo, is carbon, right? And hydrate, if you hydrate, you're drinking water, right? So a carbohydrate is anything that is carbon, hydrogen, and oxygen. That's a carbohydrate. Now, why are we focusing on all of these carbon-based molecules? That's because life is carbon-based. When NASA sends probes out to look for life, as we said, it looks for water. It also looks for carbon-based molecules because life as we know it is carbon-based. It's possible that there's alien life forms that are not carbon-based, but we don't know about them. Carbon can form 4 bonds with things, right? Oxygen can form 2. It has 2 hydrogens bonded to it. Carbon can form 4 bonds. So there are a lot of different ways that things can attach to a carbon. So here at the bottom, at the top we have methane, which is just natural gas. This is not a carbohydrate. There's no oxygen, right? So this is just the gas that you may use to heat your home or is in your stove. At the bottom here, we have a carbohydrate. It's a lot of carbons and hydrogens. And then look at the bottom, we have some oxygen. Okay. And these could all be put together in lots of different ways, right? You could have put an oxygen somewhere in the middle here, right? There are lots of different ways that a carbohydrate can be put together. So a carbohydrate is a macromolecule. Macro means big, right? As opposed to water, that's just 3 atoms put together. A carbohydrate can be really, really big. You can just keep on adding carbons as long as you want, right? Let's look at this one. I don't know how many carbons we've got here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But we could have had 20 or 100, right? You can just keep adding carbon. So a carbohydrate is a macromolecule that contains carbon and water. And these are the primary sources of fuel for our cells, right? You have to eat your breakfast to get your energy. And there are different categories of carbohydrates. Monosaccharides are simple sugars. It's just one sugar molecule. It doesn't mean it's just one carbon, but it's one molecule of sugar. And sugars tend to be hexagons, so it's like that. A disaccharide is 2 sugars, but they're bonded together, so it's a little chain. And then a polysaccharide is many. So this could be 3, it could be 1,000, okay? And then there are structural carbohydrates. They're not sugars. We don't eat them, but they form structure for organisms. So this could be like the trunk of a tree, or the shell of a cicada. So those are carbohydrates as well. So here we've got our monosaccharide, and this is a picture at the bottom that looks a lot better than what I drew. You guys don't need to memorize these structures. I'm just showing this to you so you kind of recognize and know what it looks like. I'm not going to ask you to draw them, or to I'm not going to show you a molecule and be like, name that. But a monosaccharide has 3 to 6 carbons in it. And when you eat them, the energy is released as we break apart these carbon and hydrogen bonds, right? So you break those apart and some energy comes out. So this would be if you just have a spoonful of sugar, your body quickly breaks it apart and you get a burst of energy. Disaccharides and polysaccharides are what we call complex carbohydrates because there are a few different ones bounded together, right? So if this was our monosaccharide, this would be our disaccharide, and a polysaccharide would be a really long one, right? To get energy from these, you first break apart these bonds holding together the sugars, and then you start breaking apart the bonds within the sugars. So this is a slower way to get energy, and it's more like a time release capsule. First, your body's breaking apart all of those bonds in between the sugars, and then the others, so it lasts longer. So this would be oatmeal is a more complex carbohydrate, right? So if you eat oatmeal in the morning instead of like Fruit Loops, right? It's going to give you energy throughout the day or for a long, for hours instead of just a quick jolt that you crash from. And then we have carbohydrates, which can be structural, right? So chitin, which is what insect shells are made of, and cellulose, which is what plant stems are made of. These are non-digestible. We can't actually eat these carbohydrates. They're not going to give us energy, but they add structure to things. And we still need some of that in our diet just to help our digestive system. Not necessarily chitin. I don't eat, I didn't go around eating cicadas. Some of your dogs may have when they were out. But cellulose is the roughage in our diet. So like kale has a lot of fiber in it. You're not digesting all of that, but it's kind of moving through and cleaning out your intestines. So it's still important to have fibrous diet, but it's not giving you calories. It's not giving you energy. Some organisms, however, can eat cellulose, and it is an energy source for them. So they have the ability, they have special enzymes that enable them to eat cellulose and get energy from it. Can anybody think of some animals that eat cellulose? So think for a minute. And so this would be animals that can eat wood, or that could eat like grasses and other, that focus on those. So certainly termites would be one. Oh, my pen is kind of crazy here. I'm sorry, this is kind of illegible. Termites can eat cellulose. Pandas, right? They just eat bamboo. Which is really hard if you've ever felt a bamboo stalk, right? It's pure structure, but they get their energy from that. And then there are some herbivores that have multiple stomachs that can digest lots of grasses and things like that. So that would be like deer and cows, right? So all of these organisms can digest cellulose that we can't. Now, if we look at all of these different carbohydrates, the neat thing is they all look really, really similar. Remember, I said I wasn't going to test you on what they were. It's got all the same elements in them, and it's just how you put it together. So these 4 different molecules that I'm showing you, here's starch, which is digestible, right? We eat starchy foods. Glycogen, which is sugar. Cellulose, which is plant, right? And chitin, which is an insect shell. these all have the exact same formula, which means they have, I haven't counted, but the same number of C's, the same number of H's, and the same number of O's. Let's say it's like 20 and then like 16 and 8. I don't know. All of these have the exact same formula, but depending on how you put them together, you get a completely different molecule out of it, right? And especially if you look at starch and cellulose, they just look like it's been flipped upside down. Okay, so we're going to take a break now and go into your discussion, answer the question there, and then meet me up again, and we will start talking about the other macromolecules. Bye-bye.